Alright guys, in this video let's start to take a look at what we call rational functions, or in other words, basically a function that is a ratio of two separate functions that the cool thing here is in and of themselves are polynomials. And so think about this. How many polynomials do you solve by now for real complex solutions, whatever? These are both just polynomials being divided by one another. And so in that case, let's talk about some things that we know about ratios, starting with the fact that we never want to divide by zero. So in this video, basically, what I want to start with is just finding the domain of these functions. And we're going to accept that the domain is all x values for which your denominator polynomial here, or what we call d of x, is not equal to 0. So basically, looking at this, if we want to find the domain of a function, we're basically just going to look for the zeros of the denominator, and we're going to exclude those from the domain. So when you look at, say, number 1 here, pretty easy to determine. You've got just one linear factor down here, and that only linear factor here is just x plus 1. So in that case, what we're going to find out here is that our 0 is x equals negative 1, and also that our domain then would just be the entire interval of x values, excluding negative 1 from that set. Now, as we take a look at these rational functions, what we're going to see are graphs that, and I'm going to go ahead and graph this here, that tend to exist everywhere except for at these x values for which they're undefined. And what we're seeing here is that we said that this graph was undefined for an x value of negative 1. So what I'm going to do is I'm going to put in a negative 1 here, and actually I'm going to make this a dashed line because, of course, this is an asymptote. And so this vertical asymptote, first thing I want to notice is that our graph approaches negative or positive infinities and we get really close to this x value from either side. But that being said, we would see that if you were to look at the x-axis here, all x values, excluding, of course, negative 1, would be included in this interval of values that we had listed right here. So knowing that we could just find zeros as the denominator, talk about where it's undefined, let's take a look at some other sets of domains, like number 3 here. I noticed that the denominator is a difference of 2 squares. Whenever we deal with rational functions, you should be factoring the numerator and denominator anyways to see if anything cancels. But I look at this and I'd say, well, then the zeros of this, setting both of these equal to 0, are going to be plus or minus 3 in that polynomial. So our domain, if we're listing this here, would be the entire interval of x values, excluding negative 3 and positive 3. And so it would look like this. So one question that I want to beg and ask you guys is simply this. Hey, you know, if you got 2 critical values here, how many intervals would that split your number line into? And we see that with 2 critical values, we get 3 intervals. With 1 critical value, undefined value here, we get 2 intervals. Basically, however many critical values you have, you're going to have that many plus 1 intervals, or you should for the most part with rational functions. So taking a look at these last two here, this one here, one of my favorites, we would say, what does it factor into? If you set a difference of 2 squares, x plus 2x minus 2, I got you, because here's the thing. This is a sum of 2 squares. Remember that you cannot factor a sum of 2 squares. So what would this mean? What are the zeros of this denominator right here? Well, you know, we can actually solve this by using square roots, but what we discover is that, hey, you know, you're taking the square root of a negative. We get some complex solutions. Okay, that's a 4. So we get plus or minus 2i. You guys, what this means is no real number would ever cause the denominator to be 0. And so in terms of the domain, we would see that this is some unrestricted function here. So let's take a look at these last 2 functions as we graph them. The last one there, whoops, wrong program here. We want to go to Safari. There it is. This last function that we graphed here was undefined at positive and negative 3. And I'm going to shift this asymptote here just left 3, and then we'll just introduce another asymptote. You know, there we go. A lot easier to just type x equals 3 and just be done with it. But looking at these asymptotes here, we can see that this function is defined everywhere. Sorry, I got to get this out of the way. Cancel. Is defined everywhere except for a positive and negative 3. And with respect to our next function, we said it was defined everywhere. I'm just going to take, I'm going to take these asymptotes out because you would see that this function is actually defined everywhere from left to right. Now this last function I want to look at, well, I want to look at this, well, factoring really. If we find the denominators of 0, I notice this has 4 terms here. Well, then perhaps what we could do is we could factor by grouping. You know, if this doesn't work also, and it does work, by the way, but if it doesn't work, you could always try listing out the possible rational zeros of the denominator and then just keep testing and dividing until you find one that works. So looking at our factors here, we could factor out an x squared here. I get left with an x plus 1. And then here I could factor out, well, it'd be desirable to factor out a negative 4. And so what we'll do is we'll factor that out and we get left with an x plus 1 here. Essentially, they both have a common factor of x plus 1, and some of you may have already caught this here, but this is also factorable into these 3 linear factors here, x plus 1, x plus 2, x minus 2. And so each of these is a 0 here, at least the opposite of these, so we get negative 1 plus or minus 2. But our domain, to list this out here, remember what we said, 3 critical values, we have 3 plus 1 intervals, so we have negative infinity to our very first critical value, which on the number line would be negative 2, in unity with negative 2 to negative 1, in union with negative 1 to positive 2, and then in union with 2 to infinity. So important we can find the domain here, and important that we could recognize that those undefined domain values would be these values at which we have vertical asymptotes. Cheers.